In this video, I will talk about how you can use the expression for the magnitude of the magnetic field of a solenoid. Now, it is somewhat difficult to use a 2D, to draw a 2D picture of a solenoid, at least for me. And what I did here, I'm showing you the side view, okay, and where you see these dots, there are more wires. I'm just not visualizing them. So from the side view, you see only essentially half of the loops, the wires. If you end up looking at the solenoid from this side, then you will end up seeing really only the first loop. The rest of them are essentially hiding behind this top one. So this first one is what will look like. This will be your loop, the one that you can see if you look at the solenoid from this way. Now, some important facts. This expression can only give you the magnitude of the magnetic field that the solenoid creates, not the direction. You need to find the direction using the right-hand rule. I'm gonna have a separate video about directions. Now, this expression is the constant mu naught times n, where n is the number of turns. Number of turns or number of loops, whatever you want to call them. And here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, 11, 12. So here I'm showing 12 turns, okay, or 12 loops. I is the current, the conventional current, and L is the length of the solenoid. Now, what I mean with that, this from here to here, this would be your length, and n would be the number of turns. Now, something important about the magnitude of the solenoid, we do make an assumption. This expression that gives you the magnitude of the magnetic field of the solenoid is valid only if you are near the center of the solenoid. It's not valid everywhere. Okay, this is the applicability, the conditions where this is true. You can use this expression only if you are closer to the center of the solenoid. This ends up being not true if you are close to the two ends of the solenoid, either here or here. And now a simple example of how to use it. The constant mu naught is simply 4 pi times 10 to minus 7. Let's say that I have a solenoid, 1,000 turns, a current, let's make it 0.15 amperes, and a length, let's make it 10 centimeters, so 0.1 meter. Then the magnetic field that solenoid would create inside, the constant mu naught is equal to 4 pi times 10 to minus 7. As I said, n is equal to 1,000. The current, say 15 times 10 to minus 2. And then for the length, I have 10 to minus 1. Now, to make my life easier, I will say that this is 10 minus 7 plus 3 minus 2 plus the 1 from the denominator, and then this is times 4 pi times 15. 4 pi times 15 times 10. I got minus 9 plus 3 minus 6 plus 1 minus 5 190 times 10 to minus 5 Tesla. So that will be an example, a simple application of finding the magnetic field of the solenoid inside the solenoid. We do, it is a good idea to remember, we do approximate the magnetic field that the solenoid creates outside of the solenoid to be approximately zero. So if you are anywhere B solenoid, it's not really zero, but it's very small, much smaller than what you get inside.